So we will now compute the sample size when we have random effects. So let's start with the one-way random effect. That is, we will put it in a context of repeated measures design. Okay, so let's say that we are designing a new inhalated formulation for a drug, and after giving a dose to the patient, we measure the concentration of the drug in serum. So the variance of the concentration measurements is this much, and we wonder if the patients introduce an extra variance in the process. So for doing so, we will give 4 doses to the same patient and measure the drug concentration level after each administration. How many patients do we need to study if we want to reject the hypothesis that the patient is not introducing any variability? So the null hypothesis is that the patient doesn't affect the variability of the observations, and the alternative is that it does. And we want to have a 90% of power, statistical power, if it goes as high as 25 squared. Note that this one is a bit smaller than this one. Okay, so this is a one-way ANOVA. There is a single variable that we can modify, that is the patient, but this patient is random, so it is coming from a large population of patients, and we don't know exactly what is the effect of that patient. So the formula, the observation formula, is the same as we had before. The difference with fixed effect and random effect is that fixed effects assume that these are discrete values that we are interested in. So for instance, we have 5 drugs, 2 doses, whatever, and we want to see what is the effect of these 5 drugs or these 2 doses or whatever. While in the random effects, we don't care about the person itself. So this person is just a random instance from a very large population of individuals. We don't care, well, what is the alpha 1, alpha 2, alpha 3 for these 3 particular people. All we care is that these alphas, they're introducing some randomness into or some variations on the results. And we will assume that the alphas are coming from a Gaussian distribution with some parameter sigma squared. Okay, then we have the ANOVA table. So in the ANOVA table, let's say that we have n people that we will measure r times. So the number of degrees of freedom that we need for estimating the treatment is n minus 1. In total, we will have n times r minus 1, so we have n people measured r times, so it is nr minus 1 for the total, and then the number of degrees of freedom for the errors is the difference between these two, that is this one. It is interesting to know that the covariance between any two measurements is this one, so it is sigma squared a if those two observations are coming from the same person. I is the person, J is the measurement. So if they're coming from the same person, we will have sigma squared A, and if they're coming from the same observation, so this J, we have sigma squared epsilon J. Okay, then we can compute the design, the calculation of the sample size is the same as we had before. So we have to find an f and a critical, that is the critical value, such that from that f to the left we have alpha, to the right we have alpha, from that f to the left we have beta. And the problem with the alternative is that it is non-centered, and this non-centered is the same non-centered a non-centrality parameter that we had before, that is the sum of squares of the treatment divided by the sigma of the noise. And now what is different is how to compute the sum of squares of the treatments, and this is where this covariance comes in. So you can see that this covariance somehow is reflected here. So we have sigma squared of the epsilon, that was this term, and then because we are measuring r times the same person, and each person has a variance of sigma squared a that we have here as sigma squared of the treatment, then this is the total sum of the squares for the treatments, and we have to multiply by n minus 1. Okay, so now it is simply a matter of substituting. So this is the sigma squared of the patients at which we already want to have this statistical power, and this is the sigma squared of the residuals. We have the non-centrality parameter, and we simply substitute here. We know everything except n, and then the number of degrees of freedom for the patient, the number of degrees of freedom for the noise, and then we can solve for n in this equation. That is not easy, but we will need 12 individuals if we are measuring, I think r is equal 4 here. Yeah, r is equal 4 here. Okay, what if we mix random effects with fixed effects? Okay, so let us consider the same example as before. So we are developing this inhalator for the drug, and the variance of the concentration will be this one. The variance due to the patients, let's say it is this one, and we have designed two inhalators that produce droplets of different size, and we wonder if there is a difference between these inhalators. So the inhalator is a fixed effect because we have only two values and we are interested in the contribution of each one of them. But the patient is a random effect. So for each patient we will perform 4 replicates, and what is the number of individuals that we need to study to reject the hypothesis that there is no difference in the inhalators, with a power of 90% if the difference between the two is larger than this concentration. Okay, so we are interested in a comparison on the fixed effect, but we have the randomness introduced by the random effect too. So our model will be that the measurements that we have is something that depends on an overall mean, something that depends on the inhalator, something that depends on the person, and then some measurement noise. And we will have for each one of the patients, we will have 4 replicates. Okay, so this k goes from 1 to 4. Okay, so now we have our ANOVA table. So we have A treatment, so A minus 1 degrees of freedom for the treatments. These are the inhalators. We have n individuals, so we have n minus 1 degrees of freedom for the individuals. We have A times n times r minus 1 degrees of freedom in total, and this is the difference between these two and this one. And then we have to compute the sum of squares of the treatments, these ones that we are interested in. And again, it has to do with this covariance that we had. So we have the variance of this plus, so the variance of the noise plus, this is the number of times that each one of the treatments is measured, and then times this, and then times this one. Okay, so in our design we need to find this critical f such that from that point to the right is alpha, from that point to the left is beta. So it is simply a matter of substituting. So we have 2 inhalators, r measurements, then the number of degrees of freedom for the treatments is 2 minus 1, that is 1. The number of degrees of freedom for the noise is all this, so that is 8n minus 4. The non-centrality parameter is this one, it is simply substituting, and we have something that depends on n. And then what we need to solve is this equation here, and this equation gives us 77. So we need to measure 77 people, each one of our 4 measurements, and then we will be able to tell differences. This n is per group. Okay, so 77 for one of the inhalators, 77 for the other inhalator. And yeah, and we can even include interactions. So we can include interactions between treatments and individuals or whatever. So maybe some individuals, they prefer some, so they behave differently with respect to the inhalator, and then this is the way to compute the non-centrality parameter, but we will not make any example with this. Okay, so in summary, for this second part of, or in general for the ANOVA-like experiments, the design is finding the critical value such that from that critical value to the right we have alpha, from that critical value to the left we have beta, and the key is to calculate the number of degrees of freedom that we have for the treatments, for the noise, and the non-centrality parameter that we need to know how to calculate. And that would be all for the design experiments.